Hello everyone, welcome back to Structure Expert. Today we continue to sphere frame, non-sphere frame, pref frame or non-pref frame or unpref frame. Now let's start. We will focus about the pref frame, unpref frame, sphere or non-sphere frame, and how to classify the structure. Now we classify based on the structural topology. The present or absence of the structural system. We focus about the structural pressing system. We are able to transfer all horizontal load to the foundation. These loads are wind load, earthquake, or geometrical imperfection. The structure able to reduce the transverse displacement of the overall structural system by at least 80%. It means the structural pressing system or core wall or shear wall can resist at least 80% of the horizontal force. Now we will talk about the classification based on the topology, or we can say classification based on visualization. When you see one structure has a core wall, or this one we can call it wall, and this right structure at the right hand we have shear wall in both directions. You see shear wall, shear wall, shear wall, and shear wall. So if we classification based on topology or visual, we can say that the structure is pref frame according to the wall and core wall present in the structure. This is the similar. We do not use a wall or core wall, but we use a pressing. For steel structure or for concrete structure, we use pressing. This one is the pressing in both directions, and the right hand structure is no pressing. So if we classify classification based on the visual, we do not see structural pressing or wall. We say the structure is unbraced, the structure is pressed, the structure is press frame. This is the full 3D model, also simple structure, and we cut section. You see it is the vertical column with the beam, no press frame, no press or no pressing, no core wall or no shear wall in this structure. So we call the structure unpressed or sphere frame. Now we will talk about classification based on lateral deformability. The distinction between sphere and non-sphere or press and unpressed frame is associated with frame lateral stability. The second order effects on the structural response in the term of transverse displacement. So when the structure is sphere and receives the larger deformation, so it will increase the moment, the bending moment, and the shear action on the structure or on the element. We focus on the vertical element, on the wall or on the column. A non-sphere frame is the lateral displacement are so small to give negligible increase of internal forces or moments. The presence of the pressing system. I will talk about the presence of the pressing system that can be resist at least 80% of horizontal force. And a sphere frame is the transverse displacement influence. The transverse displacement is the lateral displacement influence significantly the value of internal forces. The internal force we focus about the moment and G force. The presence of the pressing system. So if we use the pressing system, they can receive inner horizontal force. The transversal displacement. Sorry, this one is the absent. Okay, correct. It's the absent. It means no pressing system. No pressing system. If your structure don't have pressing system, and the transverse displacement influence significantly the value of internal force, moment, and shear. So we call it a sphere frame. In this process, we classification based on lateral deformability, not the same with the first one. We classify it pressure. If you see the structure has pressing system or have wall or shear wall, you can call it frame or non-sphere, or this one is unbraced frame or sphere frame. But this system classification system is not precise, is not correct. So we will focus about this system. We will give you the more precise answer. Now let's continue to geometric imperfection. In geometric imperfection, we can classify it to two different. The first one is structural system imperfection, or we can call it global imperfection. Your structure is not fully straight. It has its own imperfection of the global system. The to model this structure in the software is very hard. You cannot predict the actual angle of it. So in the concept, we can apply the force, horizontal force, multiply with the angle, or this force we can apply it as national load. National load, we can rank it to 0.2 to 0.5, or the vertical force, and combine with any combination, include the gravity combination and lateral combination. Gravity combination with load like load, and lateral combination include wind load or earthquake load. This is the value of the S1, the force of the S1 floor, S2 the force as the second floor, and S3 the force the third floor. So you use the magnitude of the 0.2% to 0.5 of the ultimate load, the load plus light load, to apply at each floor. And for the member imperfection, this one is the value of the imperfection according to the curve A0, A, B, C, D, and this is the E0, and the out of straightness imperfection. The local imperfection, you can call it local imperfection. One column is not perfectly straight. So to model this imperfection is not it really hard. You cannot model a curve structure in software. So to apply and convert this curve, you must to apply load or equivalent load. So this value of the imperfection is low. You can take it from the code, and this formula we focus for the EUROCODE. For the alpha m is equal to square root 0.5 multiplied with 1 sum 1 over m. M is the number of the column in bay, Like this one is the column in base 2, so you can replace 2. The formula is different according to the code. For the AISC and ACI code is different, but I want to explain you about concept is the same. Is applied for the geometric imperfection, for the local, and for the global. Local we apply for the notional load, and for the local imperfection we apply the value suggested from the code. For the structural system or global imperfection, you can apply notional load multiply with the you can apply the notional load vary from 0.2% to 0.5%, or the load combination gravity load, the ultimate load combination gravity load. The global and local imperfection is the geometry imperfection. These are one for the global, this one for the local. And to use the global and local imperfection, you also must to include lateral load. You can include wind, earthquake, and with the notional load. Notional load can vary from 0.2 to 0.5, or the ultimate limit state combination, or the gravity load. This is according to your code. If you use on ACI code, you can use the ultimate load according to the recommendation, and for the EUROCODE you can use 1.35 multiplied with the load plus 1.5 multiplied with light load, and you take the value and multiply with 0.2% and apply this load on each floor. Okay, is this load for the first floor. After you calculate for the load on the first floor, you can apply it, and for the second floor you can use the summation of the load in second floor and multiply with 0.2 or 0.5 and apply it at the node of the second floor, like this picture. And don't forget about modification vector reduce axial and flexural stiffness. You have to reduce stiffness. This is this one also you follow the code, and this one for the ACI code for load combination. 1.4 the load, 1.2 the load multiplied with 1.6 light load, and load combination 3, 4, and 5. Sorry, in this one is 3, 4. Load combination the load plus with light load and plus with wind load. We can design it for the p-data analysis. Include p-data analysis. You can check 1.2 and 1.05 is the gravity load, and 1.3 wind load is the lateral load. So when you do a p-data analysis, you must to include for the global imperfection and local imperfection. And don't forget about the notional load. Notional load you can apply for the lateral load combination with lateral load, or you can apply with the gravity load. If you don't know when you apply to lateral load and when you apply to lateral load, you can apply it both for the gravity load and for the lateral load. Example 1.4 the load plus 1 notional load, and 1.2 the load multiply 1.6 light load plus 1 notional load, and for the combination 1.2 the load plus 0.5 light load plus 1.3 wind load plus 1 notional load. And for the p-data effect, you can use 1.2 dl multiplied with 0.5 ll. the option used for the attempt. And for the EUROCODE, the combination 1.35 the combination for the gravity load, and the combination include gravity with the notional load, and the combination is for the lateral. You can check for the lateral include with the notional load. So the combination span is 1.35 the load multiplied with 1.5 light load multiplied with 1.5 snow, and 1.5 free zero the ratio factor multiplied with wind load and multiplied with notional load. Notional load applied for both direction 1, 2 or 8y according to your software. And I discuss in this slide. You can check to apply p-data analysis. You must to include the imperfection of the structure, must include the global imperfection and local imperfection, and don't forget combination with the notional load. And for a tab we use the p-data analysis. You can include the combination 1.35 lead load with 0.5 light load in p-data option. Now we do not know about the option in the tab. We will show you later. And for the lateral deformability for the American, this is for the ACI code. For the ACI code, in the ACI 318 in clause 10.10.5.2, the stability index Q is less than 0.5. The structure or second order effect can be ignored. So what does this mean? If the stability index Q is less than 0.05, you can consider the structure as the non-sway, or you can call in the European country call it a frame. The three report does calculate an indicative stability coefficient delta 2 over delta 1. The moment magnifier from the ACI code, delta S is equal to 1 over 1 minus U. So if you the question 1 over 1 minus Q is equal to, this is the indicative stability coefficient, delta 2 over delta 1. So you can calculate the value of the delta 2 over delta 1 is less than 1.0526. So if you use if you calculate the trish, okay, the tree delta 2 over delta 1 is less than 1.05. So you can assume the frame or this element is non-sphere. What is delta 2 and delta 1? Delta 2 is the trish calculated based on the second order effect, and the delta 1 is the trish calculated based on linear analysis. And the accurate determination of second order effect for the concrete, it depends on the concrete long-term property. So you must to modify your stiffness, modify for the concrete, modify for the flexural and axial stiffness. Now let's jump into the EUROCODE. The EUROCODE, we talk about the amplification factor. Amplification factor, the formula we use for the structure. The structure with clad and stiffening effect of the cladding is not taken into account. So you can use the formula. Otherwise, you can use the amplification factor is equal to lambda critical over lambda critical minus 1. And is lambda critical is greater than 10. So the second order effect can be ignored. And you can read it. I write it, and you can read from 1, 2, 3, and 6. Now I summarize it for you. The design flow, EUROCODE, run analysis. The first one, we run the first order analysis, linear analysis, and check for the member size. Okay, if the member size, the section is enormous, you can continue to analyze in design. If your section is not enormous, you can change the section. We use the first order analysis and calculate the critical lambda critical. If lambda critical is over 10 over than 10 or lower than 10. Now check is the value is lower is greater than 10. We can continue to design. You can use linear analysis to design, to analyze and design, continue to design. If the critical lambda critical is not greater than 10, so the value is less than 10, you must check. If critical lambda critical less than 2, you have to remodeling your structure. You have to add more wall. You have to add more pressing. You have to change your column section. You have to add extra thickness on your structure. And if your lambda critical less than 2, but in rank 2 or 3, you can refine. Okay, you can add more stiffness on the structure until the value of lambda critical greater than 4. The value you can limit it 3 or 4. You can limit it 3 to 10. Now I limit it in 4 to 10. If you calculate the lambda critical is greater than 4 and lower than 10, you can do full second order analysis and design. So you can check it. The design flow, you can run the first order analysis in case all the your structure has a lambda critical greater than 10. And if you check the lambda critical is greater than 10, you can continue to design. But if value is not greater than 10, is lower than 10, you must to check the value of lambda critical. It's a rank lower than 2 or greater than 2 or in rank 4 to 10. If the value is rank or 2, you must to remodel the structure. So if in this rank, some time you can limit it in 3 to 10. You can do full second order analysis and design. Now we continue to classification based on lateral deformability. Now the moment second order effect M2 over M1 is lower than 10 for the EUROCODE, and critical lambda is over 1010. This structure is non-sway or flat frame. In the Europe, they call it flat frame. For the ACI code or American code, it is second order moment over the first order moment. The moment you run in linear analysis is lower than 5%, and the delta 2 over delta 1 lower than 1.0526. You can call it non-sway frame. This is the example for the first moment. We have a cantilever column applied with horizontal force and vertical force, and the column height is h. When you apply the lateral force S, the structure will deform the delta. This delta is big delta. And for the first order moment, you can apply the S1 multiply with the level arm. Level arm is the H. Now M1 is equal to S multiplied with H. Okay, S1 multiplied with H. And the big data you can use the formula to calculate for the cantilever column. So M2 is the second moment, second order moment. Second order moment, you can use the formula. The first order moment apply with the n multiplied with the big data. And is this value greater than 0.1 multiplied with the S8 is the 0.1 or the first order moment, you must to include second order effect. And it is similar when you apply moment at the top. You can use the formula, and the verification is the same. If over 10 then 10% of the first moment, you might include the second order effect. And fourth moment M1, okay, it's the same with the about slide, but now we want to focus about small data. Small data. If we talk about small data, we must to talk about the slenderness. The slenderness effect, we will talk about the long column. The column, we can classify it to short column and long column. For the long column, we concern about the slenderness. So the slenderness, we have to include the small data. For the short column, it's not concerned about the small data. In 1744, Leonard Euler divided equation. The equation, the n is equal 1, the Hasind, okay, the Hasind, n is equal 1, the Hasind for the isolated member with pin support. He make experiment by using the isolated member. So n is equal 1. This is the shape of the deformation, and is n is equal to the shape of deformation, and is n is equal 3 the shape of deformation. And the effective length factor is equal to 1 divided n. So in the case is n is equal to 1. In the case n is equal to 2, 1, 2. the case n is equal to 3, 1, 2, 3. This is the critical load. And we want to talk about the single curvature and double curvature. You have to know about the single curvature and double curvature. What is single curvature and what is the double curvature? This deformation shape is for the single curvature, and the moment like this one. And for the double curvature, you see here, the shape is like this one, is like the n is equal to the double curvature, and the moment we have two sides, m2 and m1. And for the single curvature, we have only one side, m1 and m2. In one side, in this one is two sides, m2 and m1. And for the single curvature or double curvature, we will continue to discuss about this topic. Now let's talk about single cantilever column. We not talk it as a frame. It's a single element, a single cantilever column. And the picture below is multi-story building. Now let's check about a single cantilever column. We can include for the big data and small data. So this moment made by the first order moment, and this moment made by the big data, and this moment made by the p multiplied with the small data, and we can call it p data. Now in this symbol we use n is equal to p, and the total moment we sum of the three moments. You can check for the bending moment for the big p data, small p data, and for the first moment, first order moment. And for the single cantilever column, for the single, the deformation all over in a single curvature. You check here. This shape of deformation is single curvature, and its moment is like this one. It also a single curvature. You can check about the moment shape, one side, and for double curvature, two sides. Has a m2 and m1 in opposite side, and for the single curvature, m1 and m2 is the same side. Now you observe on the deformation shape of the element. For the single element, apply the horizontal force or lateral force with the vertical force. You can observe about the small data. And now let's talk about multi-story building. Multi-story building is similar, but it's not the same with the single member, because the deformation shape like this one. You can check the deformation shape is in the ball curvature. It's like the ball curvature. It curve, but its value is data, small data is equal to 0. We have another data in this location, but the value of data is smaller than the single element. The single element we concern about the big data and about the small data. For the frame, for the building, the value is small if you compare with the single element. But in the design code, you can verify it, use it to check the small data by using the formula recommended in design code. This is for the concept of structural analysis. And in a tab, you can assign one column with the auto main option. Assign it to different main option. You can assign it the value of main option. The is equal to the the width of the column. Why we want to assign automate option? You can divide the column into, example, I want to divide the column into 20 different segment. 20 segment. It is really hard to divide your column, so you use the option to assign the mesh in a single element. You can compare each other when you do not assign the mesh. Okay, assign the automate option in a tab. The tab we model it in this model we model it in a tab. For the WordPy analysis in design, you can check in my tutorial. And last picture, we do not include the automate option. You can check the moment. And the right, we include the automate option. You can check the map from 1 to 1. And this one for the M33, you can check when we assign the automate option. So when you want to include the P data, you have to use the option to check for the small data, to active and check for the small data in the tab. We will calculate it's more better when you use the option. And if you do not use the option, your result is not accurate. It has another different result from assigned with the automate option. And the critic event design also have automate option. You can check it. Now we continue to talk about big P data and small P data. You can see the last picture. When we talk about big P data, you see apply load at the top. When we have restore load apply, so we will have another big data. And big data, we can talk about the global deformation or global imperfection of the structure. And for the small data, we talk about the loophole, about the column, one element. We not talk about the global, we talk about the element. When you talk about the small data, we talk about the element. We talk about the column, or we talk about the wall. We talk about the vertical element. And for the long column, we concern about the small data for the long column. You can check the frame. And now for the short member and non-sphere, all other effect can be ignored. So you can analyze and design without include the notional load, include the geometric imperfection, not include the global imperfection and local imperfection. You can design it, analyze it, and design it in linear analysis. After you run linear analysis, you can direct to design it if your column is short member. And if your column is short but is square, you have to include the member effect. Okay, member effect, the member imperfection. But for the global imperfection, no need to take into account. For the slender member but non-sphere, sorry. Now we talk about sphere with non-sphere column. For the short column non-sphere A, all second order effect can be ignored. You do not need to include the global imperfection or the member or the notional load, you just run in the linear analysis. After you analyze in further analysis, you can continue to design for the member for the column non-square. The column is a short column. In case the short column non-square, you can run in linear analysis and direct to the design. For the B, the slender member but non-square. Slender member, you can call it long column but non-square. Global fix can be ignored. But member fix must be considered. Member fix is the small data. Small data must be considered. For the global fix, big data you can be ignored. And for the C, short column but square, global fix must be considered. You can consider all the effect of the global imperfection. And member fix can be ignored. For the small data you can ignore. And for the D, the slender member or long column and square, you must to include all global effect and local effect for the big data and small data. To include all big data and small data, don't forget the notional load. Don't forget about the notional load to apply for the whole structure. Okay, notional load and member imperfection. You can check in my slide. We talk about the global imperfection and local imperfection. Okay, you must to include geometric imperfection. Now let me summarize for you. For the column type is short non-square. Global imperfection no need to include. Local imperfection you can include it because for the column, for the vertical member, we can include the minimum eccentricity. For the notional load, no need to include. You can run in linear analysis. And for the big P data and small P data, not include in analysis in design. So you can run the linear analysis and continue to design. For the short column and square, for the global imperfection, no need. For local imperfection, for the minimum eccentricity, you can include it. And for notional load, you can apply or not. Yeah, you can apply. If you want to apply, you can apply it, or you can not apply it. It's acceptable. For those two options, you can apply or not apply. And analysis, you can run in linear or non-linear analysis. And for the big P data, not include. For the small data, you can include it. But for the short member, the effect of small P data is too small. For the long column non-square, for the global imperfection, not include. For the local imperfection, yes, you have to include. For notional load, no need to apply. And for the linear analysis or non-linear analysis, you can analyze it in linear. And P data, big P data, no need to include. And small P data, yes, must be included. For the long column, you must be consider about the slenderness, P data, P small data, the slenderness effect. For the long and square, you must to include it all. you must to include for the global infection, local infection, apply notional load. Okay, for the active or global infection or local infection, you have to apply for the notional load. And analysis type, for the accurate, we must to run in non-linear analysis. And the column we analyze include the big P data and small P data in the software. You can include the option, or in design it manually. You can also include it in your structure for the long way. Don't forget the concept apply for two direction. One section has its own measure ACI and local ACI, so we apply in both axes for the measure ACI and local ACI. Big P data, the global effect, global deformation, and P small data, local effect, member deformation. If you use if your PC is really super fast, you do not care about the how it runs. Okay, you can click it and it complete your analysis design. So you can use the option active is all. Active is all. You really hard to classification. Which one you linear analysis, which one you non-linear analysis. When include P data, big P data, and when include small P data. So you can include it all for global infection, local infection, notional load, and run it non-linear analysis, and include big P data and small P data. To apply the option, don't forget about use the option. Okay, you active big P data and small P data, and apply with the automate option to assign small member. Okay, it's the same with you divide it as small member in column. You can divide it to 20 or 30 in one column, divide it to a small segment, but instead of you use the option to divide, you can use frame automate option. You will got a more better result. Include all the analysis result, bending moment, shear force, shear force with the deformation of the member. So the option is really good for you for the long column. You concerned about the slenderness, about the small data. You can use the option.